Hi. Good morning, everybody. My name is Ilya. Thank you very much, Tammy, for the introduction, and also a big thanks to all of you for coming here. So Lisa did a fantastic job of describing the topic of gravitational wave astronomy and, of course, introducing how our detectors work, which is great because, as you will see in a couple of slides, my picture of how our detectors work is slightly primitive. But I will try to tell you, hopefully, why we, as astrophysicists, are so excited about this discovery and what we're already learning from it and what we hope to learn from future gravitational wave observations once we have a large population of these observations. So how do we go looking for black holes, right? I'll figure out how to do this eventually. So, well, you might think that the way that astronomers work is they stare up at the sky and they see some electromagnetic waves. It's very exciting. There's some light coming down. We see a beautiful galaxy. Life is wonderful. Well, modern astronomers work a little bit differently. Modern astronomers actually put a telescope on some remote platform somewhere, or maybe even on a satellite, and the data goes down to a laptop, and then there's some graduate student that is working away at this laptop, and eventually, hopefully, figures out that there is, some very exciting stream of ones and zeros that is sufficiently interesting to write a paper about. And that beautiful galaxy is kind of a side note now. So let's now talk about looking for black holes. There, that's a black hole. Great, we've seen it. Right? Done. Sorry. Unfortunately, this is the end of the talk because that's all there is to see, folks. Right? So it's hard to see a black hole, right? By construction, the reason we call them black holes is that they are so dense, right? They're singularities in space-time that nothing, not even light, can escape from the vicinity of this incredibly dense region of space. So it seems that we're kind of out of luck. Well, maybe we're not completely out of luck because maybe there are some ways to do this after all. And here's one of the ways to do this. Does anybody recognize this image? Right, so this is from Interstellar. We'll actually get back to Interstellar in a moment. But the basic idea here, we won't go into any details, but for those who haven't seen this picture before, right, the idea is that there is a very massive black hole here. There's a disk of matter going around the black hole. It's actually being lensed by the gravity of the black hole, which is why you see this very strange configuration over here. But the basic picture is black holes on their own are very hard to see. But if there's matter around them, then you might actually be able to see light from the matter going around the black holes. And this is, in fact, one of the ways that we've known that black holes existed long before the LIGO discoveries. So here is a look at the center of our own galaxy, the Milky Way. So we're looking about 25,000 light years away in a region known as Sagittarius A because it's sort of near the Sagittarius constellation. And there are some stars over here which you can barely resolve, but people working at several different institutions, in particular people working at UCLA and using the Keck telescope, have figured out how to use something called adaptive optics to really improve the resolution of things in the galactic center. And what they've been able to do over the last several decades is track the motion of stars in the galactic center. And what they see is something like, hold on, this was supposed to be an animation. Yep, there it is. So this is what they're actually able to see once they turn on this thing called adaptive optics. They can hugely improve the resolution, and that allows them to track the motion of stars in the galactic center, and they're able to see something like, will this start? Yes, something like this. So this is now an animation. Stars don't actually look like funny circles like that, but the basic idea that you can see over here, and the year is sort of clicking up in the upper right-hand corner, so this was about 20 years worth of data, but you can see these stars moving on orbits, just like planets moving around the sun, for example, except that if you try to calculate what is the mass of the thing that they're moving around, because you can do that by using Kepler's law, just knowing the size of the orbit and the period of the orbit, you've realized that the mass of this thing that they're moving around is about 4 million times more massive than the sun. And it's confined to a very, very, very small region of space. And so you ask yourself, well, if I put 4 million stars in there, well, first of all, it's very difficult to actually fit 4 million stars in there. But even if I somehow managed to, I would see this incredibly bright object. There's nothing there, right? You see these little stars, I mean, not so little, they're a few times more massive than the sun, but you can resolve these individual stars that are a few times more massive than the sun, and you don't see this 4 million solar mass thing. That seems pretty perplexing, right? And in fact, the only plausible explanation we know of is that there is a very massive black hole, 4 million solar mass black hole, sitting right there in the galactic center. So this is one of the ways in which we know that black holes really do exist. Of course, another way, as Lisa already told you, is to try to look for gravitational waves. These ripples in space-time that propagate outwards like waves in a pond, and that are, in fact, generated by very fast-moving concentrations of matter, cause space-time to be stretched and squeezed. So if you are thinking of trying to look particularly appealing to your partner, for example, then you might ask for a gravitational wave to come along just at the right time. You might look a little bit taller and a little bit slimmer because the gravitational wave stretches you this way and squeezes you this way. Just make sure that when you do this, you tell the partner to look at the right time, because unfortunately the next half cycle you'll be stretched this way and squeezed this way. You also had better hope that your partner has very good eyesight, because as Lisa told you, the typical gravitational waves we are likely to detect here on Earth will stretch you and squeeze you by 1 part in 10 to the 22nd, so might be a little bit tricky to see. But in general, the idea is that the strength of the gravitational waves, the timing of the gravitational waves, their shape, if you wish, tell us something about the nature of the objects that created them. So now we have, this is my picture of gravitational wave astronomy, right? This is why, Lisa was giving the first talk, not me, for a very good reason, because as far as I'm concerned, there's something that happens out there. I'm very interested in that. Then there is this thing over here that's, okay, in this case it's the Hanford, Washington site, so that's a LIGO detector there. See, I could at least tell which site it was. I've been there. I even got to be in the control room a few times. They let me. I didn't destroy anything. That was very good. And then data comes to a computer, and then I get very happy, right? Okay, so that's my operational picture of how gravitational wave detectors work. So the stuff that I'm going to try to focus on is what happens out there, not here on Earth when we detect them, but out there. What is it that creates these gravitational waves? And in particular, how you form these binaries of two compact objects, neutron stars or black holes. You need these objects to be quite compact, by the way, in order to generate gravitational waves that LIGO is sensitive to. Remember that Lisa said that there's a seismic wall at about 10 hertz. So that means we cannot detect gravitational waves at frequencies below 10 hertz. That means that these things must be going around each other several times per second in order for you to be able to detect them. So we're talking about very massive things that are typically at least as massive as the sun, maybe tens or even hundreds of times more massive than the sun, and they're zooming around each other a few times per second. That means they have to be very, very close together. You cannot just take two normal stars and put them this close together. They're going to, they will actually merge and form a single star, because you'd have to put them so close together, the distance between the two stars will be much, 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 much smaller than the size of the sun. It's actually much, much smaller than the size of the Earth, is the typical distance between these two things by the time they're in the band of the LIGO detectors, right? So you are now forced to deal with situations where the two stars have already formed very compact objects. A neutron star with the mass 1.5 times that of the sun is only about 10 or 12 kilometers across. A black hole is, black hole is a point in space, but the event horizon of the black hole is going to have a radius of about 3 kilometers for a 1 solar mass black hole, right? So these are indeed extremely compact objects. Oops, sorry, that was slightly premature. So what I was going to say was that let's see, this actually does work. I'm impressed. Okay, good. So what I was going to say was that of course Lisa showed you wonderful pictures of gravitational waves. I'm going to try to play to you what the sound of a gravitational wave looks like, or sounds like, because I think gravitational waves, really, you should think about them as a bit more like sounds than like pictures. It's true that space and time are getting stretched and squeezed, but that's sort of what, in a funny way, what sound waves do. Of course, it's not sound. You're talking about gravitational waves in vacuum. But one of the really nice features here is that gravitational waves in the LIGO band are actually in the audible band. You're talking about things that are, let's say, at 100 hertz. That is something that, as you will see in a moment, or hear in a moment, we can really listen to. And this is really going to be a fairly exact representation of what gravitational waves ought to sound like. We didn't change for this animation the frequency or the phasing or anything else. The only thing we did was put them into a sound file and increase the amplitude a bit. But if you have an experience as a submarine sonar operator, for example, then I'm sure that, and you're very, very sensitive, I'm sure the LIGO collaboration will be very interested in talking to you some more. So there it is. Did you hear that chirp? By the way, I don't know if this is still the case. I'm no longer in the LIGO collaboration, but when I joined, one of the tests to determine whether you were allowed to be in LIGO collaboration was whether you could make the gravitational wave sound, right? And it's very simple. You just go, right? That chirp is the really key feature of gravitational waves from two merging compact objects, because as the two objects are going around each other, they're losing energy through gravitational waves. The frequency of the gravitational waves reflects the frequency of the orbit. For a circular orbit, it's actually twice the orbital frequency. The amplitude gets bigger and bigger as the objects come closer and closer together. There is a stronger interaction as they get closer together. And as the energy through gravitational waves goes out, of course, it means you're taking energy out of the orbit, so the orbit shrinks. So let's say two black holes come closer together. So what does that do? Well, it increases the amplitude because as they get closer together, they interact more strongly. And it increases the frequency because as they get closer together, they go around each other faster and faster and faster. So that means that over the course of the gravitational wave, over the course of this in-spiral of two objects, you actually sense that there's a constant increase in both amplitude and frequency, and this is this characteristic chirp that you've just heard. And by the way, I'll play you another chirp in a moment of two objects with somewhat different masses, and you'll hear that the basic features are the same, but it sounds a bit different. The evolution in terms of in time is a little bit different over here. So these are more massive objects, 14 and 50 solar masses. The previous one was 1.4 and 10 solar masses. And so hopefully you got a sense from this that, yes, this chirp pattern is still there. You're still increasing in frequency. You're still increasing in amplitude as the objects spiral in. But there's a difference in the details of the signal. And that's what Lisa meant when she said that you can infer the properties of the sources from the gravitational wave signature, right? Because the signal here for a different combination of masses is a little bit different, that means you can, once you actually have the gravitational waves, you can go and say, so what were the masses of these objects, right? And that's very important. We don't want to just detect gravitational waves. We want to learn something about what were the objects that generated those gravitational waves. So this is the paper that Lisa, of course, has already referred to, the paper that announced the first detection. I actually wanted to highlight one particular aspect of this. So when this paper first came out, some of my colleagues at the University of Birmingham in England, who are particle physicists and who work on at the Large Hadron Collider, they said, so how big is your collaboration, relative to the size of some of these particle physics experiments? And they told me that it's only a real collaboration if there's somebody in the author list starting with every letter of the alphabet. So I did this check, and there's a very long author list that spans multiple pages. I couldn't possibly put it up. But I noticed one thing here. I noticed that there is Wu and then there's Yablon, and there's nobody whose last name starts with an X on this author list. So that means that if your last name starts with an X, the LIGO collaboration definitely has room for you. All right? Okay. I know Lisa has already shown pictures like this. I just couldn't resist because this is so beautiful, this fantastic gravitational wave signal that you see where you really are able to very accurately reconstruct the signal, and it matches so well with our predictions from numerical relativity, which is basically a way of exactly solving Einstein's equations on a supercomputer. And of course, you also see these black holes spiraling in together, right? So these represent sort of where you are as the wave. So the waveform essentially reflects where you are in this course of the binary evolution. So here you're still fairly a few cycles before merger. You still have two distinct black holes. And then here you have the merger where the amplitude peaks and the two black holes have come together. And then you actually have a single black hole that that's a little bit perturbed and sort of shakes around for a while, going, kind of like a dog getting out of the water, right? You can get rid of a bit of extra nonsense that gets piled up on it during this merger, because black holes are these wonderfully perfect objects. They're among the most perfect and simple objects in the universe, right? I mean, a black hole is described by two numbers: its mass and its spin. That's it. You basically can't imagine sort of anything that's more simple in a way than a black hole, or more complicated at the same time. And this is what makes them so wonderful. And by the way, you can also see from this plot that by the end of this, they're also moving around each other at about half the speed of light, which is also kind of insane. But anyway.
What is ring down?
Oh, so what is ring down? So this ring down is this dog getting out of the water effect, right? So it basically says, look, a black hole should be this very nice, simple object that's just described by its mass and its spin. But initially, when you've merged two black holes together, the new black hole you formed looks a little bit lumpy. It's not this nice, perfect, almost spherical object, right? And it tries to get rid of this extra lumpiness. It sort of shakes a little bit, and that actually continues to radiate gravitational waves until it settles down into its pristine black hole state that it wants to be in. So these are, the formal name for these things are quasi-normal oscillations or quasi-normal ringing, and ring down is kind of the simplified picture for it. So now, hopefully, by the way, you can feel like you're one of the cognoscenti and understand this little silly cartoon. So for people who are sitting in the back, this is taken from the New Yorker shortly after the detection, and you probably know the New Yorker sort of prides itself on putting in these cartoons where the vast majority of the people have no idea what's going on. But if you actually manage to figure out what's going on, then you feel like, I'm one of the cool kids. I understand this, right? And I basically understand about 1 out of 10 cartoons in New Yorker. I don't know about the rest of you, but when I do understand one, I feel so proud of myself. So now, when you see this New Yorker cartoon, you can also feel proud of yourself, right? Was it you I heard just now, or were the two black holes colliding with two birds drawn there, right? So now you know it's all about the chirp of the black holes, right? So this talk was at least useful for something. You can understand this New Yorker cartoon. Okay, so where do these things come from? They come from the planet Tatooine, right? So if you look at this, you might say to yourself, okay, this is a bit insane, right? George Lucas was a visionary, of course, but it's all science fiction, right? What's up with these two stars over this planet Tatooine, right? And then you actually realize, no, this is not an exception. This is perfectly normal. It's we who are an exception. Stars don't like being alone any more than people do. They like pairing up. Sometimes stars do even kinkier things. They go into for threesomes and foursomes and so on. We won't talk about that. But they really do, especially massive stars. They're kind of a little weird that way. But certainly binary stars are run of the mill. In fact, the majority of stars are in binaries, not in single systems. Our sun really is more an exception than the rule. So it's quite common for stars to be in binaries. So let's ask what happens if you put two massive stars in a binary. So here are two stars. Let's call them Stella and Estelle. Those are both sort of stellar names in one way or another. And so they're pretty, two happy stars. And they aren't just stars they're actually rock stars. They're the rock stars of the stellar world because they're massive, right? So these are stars that are, let's say, 30 times the mass of our sun. Now, massive stars, there's a few ways in which they're like rock stars, and one of them is that, like rock stars, they have an unfortunate tendency of burning bright and dying young. These stars are a lot, literally, they're much, much, much more bright than our sun is. They're very blue and very luminous, but also they have really short lifetimes. They are so bright that they manage, even though they have so much more material to burn through, they burn through it so much faster that a very massive star might only live for about 3 million years. Whereas something like our sun has a lifetime of about 10 billion years. We're roughly halfway through it, so 5 billion years of burning already, 5 billion more to go. By the way, when I say burning, I apologize. This is, of course, not burning as you might do when you're roasting marshmallows on a campfire. This is actually thermonuclear explosions. So our sun and all of these stars are basically sort of non-stop hydrogen bombs constantly ticking. What they're doing is they're fusing hydrogen to make helium, at least on the main sequence. Later on, they go on and continue fusing helium and carbon and oxygen and neon and all the way up through iron. But at least when they are initially born, they're mostly, and for most of their life, they're fusing hydrogen and producing helium as a result, and that generates a thermal energy which is able to keep the star from collapsing, right? Because the star naturally wants to contract, because, of course, the outer layers of the star feel the gravitational pull of the inside of the star. The star wants to come together, and it's this production of thermal energy through these nuclear processes that is preventing the star from contracting, right? So the star is in some kind of an equilibrium. But these stars, they're going to burn very bright, and they will sadly die young after only a few million years, which by astrophysical standards is peanuts. And, well, they're rock stars in other ways. So one of the ways in which they're rock stars, you see all this confetti out there that's coming out. That's because they emit huge amounts of wind, basically gas, from their surface. So you may have heard of solar wind, and solar wind is something that potentially can wreak havoc with satellite systems and so on. These things are so much worse, right? I mean, the sun, again, is kind of boring. I mean, we really, yes, we're kind of fortunate to be here. It would be kind of unpleasant to be next to one of these guys, but it's also kind of unfortunate that the sun just, does its own little thing very, very slowly. If you actually calculate how much energy the sun generates, you realize that even though I talk about it as a constant hydrogen bomb going off, a cubic meter of the sun produces less power than a light bulb, right? So that's kind of sad, right? These things are awesome, right? These things, when they lose mass, they really go for losing mass. They can lose the equivalent, in some stages of their evolution, the equivalent of something like the mass of the sun in a century, maybe in 1,000 years, right? These things are pretty impressive. Now, sadly, even for these impressive rock stars, sometimes, as they get a little bit older, they begin to expand a little bit, right? Their waistlines start to bulge a little. The real reason that this happens, the real reason the stars expand is something like the following. Again, it's a slightly simplified picture, but bear with me for a moment. So remember, the reason the stars were not contracting, despite the gravitational pull, was that we were generating energy on the inside. We were converting hydrogen into helium. At some point, you run out of hydrogen in the center of the star where this burning is happening. So you end up with a core of the star, the center of the star, which is just made out of helium. You still have some hydrogen on the outside, but on the outside, the temperature and the pressure aren't quite hot enough for you to be going through this nuclear reaction, the hydrogen fusion. So the core now is experiencing a lot of pressure. There's a strong gravitational pull, and there's no energy input to counterbalance it, so it starts to contract. And as the helium core contracts, now you are releasing energy. This is the gravitational binding energy. It's much more favorable to be compact than to be extended. So you're releasing energy. This energy goes ultimately into the envelope, this envelope of hydrogen, the shell of hydrogen that was sitting on the outside, and it starts expanding this shell of hydrogen. And so this is how you convert your nice, reasonably compact star that was, let's say, a few times the size of the sun, because these were massive stars, into a giant which may be much larger than the distance from the sun to the earth. So it can be hundreds, maybe even thousands of times larger than the sun. So when that happens, if these two stars are in a binary, of course, if one of them starts expanding, usually the more massive one will start expanding first because it evolves more quickly. As it starts expanding, it's beginning to become more and more sensitive to the pull of its companion. Because as you get bigger and bigger, your own self-gravity becomes less important. And now, as it's expanding, parts of me come closer to you. And now your pull on this side of me becomes actually stronger than the internal difference in my self-gravity. Essentially, you're raising tides on my surface, just like the tides that the moon is raising on the Earth's oceans. But imagine tides that progressively get larger and larger and larger until the tides get so big, if you put the moon very close, it's actually going to start ripping off some of the water from the oceans, from the side of the ocean that's closest to it, right? So eventually you start transferring some mass from one star to the other. So the binary begins to interact. All kinds of interesting processes can happen during this interaction. For example, depending on the rate of this mass transfer and the configuration of the two stars, what might happen is that this mass transfer might even become unstable. As I transfer more and more mass, I only get bigger in the process, and your pull on me gets greater and greater, so I want to transfer even more mass. So it's sort of a runaway process, a dynamically unstable process. And for the purposes of keeping this talk PG, we're going to call this a common envelope. So we'll put an envelope over it, right? This is the common envelope basically says at some point, if the mass transfer really becomes dynamically unstable, you're pulling all of this mass from you at a very high rate. It doesn't have time to actually go onto the companion star. It just gets blown up into a big cloud of gas around both stars, which is effectively screening the stars from view to a large extent. And so that's the common envelope, so that we're not staring at the two rock stars too closely while they're interacting. Interaction is the official scientific term. By the way, this is actually a picture. Well, let's say not an entirely accurate picture, but it's an artist's impression based on natural observation of two stars that really are going through a Roche-Lobe overflow process. So Roche-Lobe overflow is, again, the technical term for matter being blown off of one star and going onto the other star. In this case, actually an accretion disk, a disk of matter around a compact object companion. Okay, so then at some point, something else can happen to one of our stars. Sadly, at some point in its life, when this rock star gets a bit old, you can see that the hair color has changed. You see, look at the gray hair. It used to be in the cool and purple. Now the star is getting a little later in its life, and that means that it has gone at this point. Not only has it converted all of the hydrogen to helium in its core, but then it went on and converted its helium into carbon and into oxygen, into neon, into silicon, ultimately into iron. And once you get to iron, it actually turns out that there is no point in going further. Because up until you get to iron, you generate energy by going through fusion. After iron, if you did, and sometimes you do manage to go a bit beyond iron, right? So you go to, let's say, uranium or plutonium, right? At that point, you're actually putting energy in to do that, and you could produce energy through fission again. But iron is sort of the most stable element you can have around, because anything less massive, it's energetically efficient to fuse it. Anything more massive, fission is the energetically efficient process. you stop at iron. So once you've stopped at iron, once your core is now made out of iron, now there is really no more nuclear burning going on. So you kind of can't keep this thing from collapsing. And now what happens depends a bit on the mass of the star. If the star had a relatively low mass initially, we think roughly between 8 times the mass of the sun and 20 times the mass of the sun will do it, but the boundaries are a little bit unclear and depend on some of the details of these interactions. But if it's between 8 and 20 solar masses, it will become a neutron star. So a neutron star is a star that is very, very compact. It's only about 10 to 15 kilometers in radius, but it's not a singularity. It's not a black hole. It doesn't have an event horizon. There is still matter, just matter at nuclear density. It's incredibly dense, but it's still, in some sense, a normal star with a surface and all the behavior you might expect from a normal star, except that it's not supported anymore by, let's say, the normal internal pressure that you might expect. It's instead supported by something called the Fermi degeneracy pressure, which is a kind of quantum mechanical pressure. It basically comes about because neutrons in the neutron star being fermions, being spin 1/2 particles, don't all want to sit in the same energy state in a very confined space. So this is a quantum mechanical phenomenon. They start elbowing each other, they're pushing out on each other, and they demand some minimum volume to sit in. And it turns out that for the masses involved, for a neutron star, about an object about 10 to 15 kilometers in radius is sort of the minimal volume they require, and that's where the collapse stops. But if you're even more massive than 20 solar masses initially, then I'm afraid most of the time your fate is sealed. You end up collapsing into a black hole. Nothing, not even the neutron Fermi degeneracy pressure, is going to prevent you from collapsing. But Thierry is going to tell you a lot more about how this process happens later in the afternoon, and will also clean up any of the misconceptions I have left behind in my very oversimplified analogy. So I apologize, Thierry. Thierry works specifically on things which I'm going to just show here with a single picture. Right? This is the nebula left behind after a supernova. Because what I've just described to you now, this process of a rapid contraction into a neutron star or a black hole, is often accompanied by an explosion where the outer layers of the star are sent off into space at a very high velocity. And this is the picture of what you're seeing here. This is a remnant from one of these supernova, a so-called nebula. Okay, so now let's put all of this together, right? We've sort of talked about some of the things that happen with two stars. So let's try to put this together. And okay, well, oh yes, we had a black hole, exactly. Somebody was paying attention. We had a supernova explosion. In this case, it did leave behind a black hole. Okay, so now let's try to put this together. Yes, fantastic. Sorry, I had forgotten I had another black hole in there. Okay, so this is a diagram from a paper that some of my students have recently written, and it follows lots of work by many other people who have produced similar kinds of diagrams showing this evolutionary process. So Chris, who is sitting over there, for example, and who will, I think, be the chair for the next section, he and his students have produced, I think, an even prettier picture of this diagram in an earlier paper. But this is what this evolution might look like for the event that Lisa started out describing, this so-called GW150914 event, the merger of two 30 solar mass black holes. By the way, how much time do I have left?
10 minutes.
10 minutes, perfect. Okay, so what you have over here is that you start out with two fairly massive stars. The stars lose a little bit of mass through winds, right? They're almost 100 solar masses each to begin with, 100 times the mass of the sun. Then this star begins to expand. It starts transferring mass onto its companion. This is this overflow of mass. The companion goes up in mass. This star, of course, shrinks. It loses maybe half the mass during this process, essentially its entire envelope. Then this collapses to a black hole. The stars, by the way, during this whole process are quite far apart. They're about 2,000 to 4,000 times the radius of the sun apart, so that's about 10 to 20 times the distance from the Earth to the sun. That is how far you kind of have to put them apart initially, so they don't just start merging during this process, so that this mass transfer can still be stable and leave the stars separate. On the other hand, you've got a bit of a problem, because if you have them that far apart, if they form black holes right then and there, they will never merge within the age of the universe. Gravitational waves aren't that efficient at losing energy until or unless you bring the black holes pretty close together to no more than a few tens of solar radii apart. So that means you have to bring these two black holes closer together somehow, and it turns out that this common envelope shown here is the way to do it. Because you start transferring mass from the second object to the first object, to this now formed black hole, and this process is one of these dynamically unstable mass transfers. So you've created a big cloud of gas around the core of the second star and the black hole, which you've already formed here, and now you've got these two objects, the core and the black hole, moving inside this dense envelope of gas. And as they're doing it, of course, there's a lot of friction against the gas. They're pumping energy into the gas. Eventually, you pump in enough energy, you heat up this gas cloud enough that you actually manage to eject all of the gas from the binary. But in the process of doing so, it's taken you quite a bit of energy to do that. That energy comes from the binary's orbit. So that means that your binary, your pair of black holes, will actually come closer together. The binary shrinks. It shrinks a lot. It shrinks by something like a factor of 100 here. So you go from 4,000 in this particular example solar radii to 34 solar radii, right? And this is fairly typical for what might happen during a common envelope phase, this shrinking by something like a factor of 100. And so now you end up with a black hole and a stellar core fairly close together. Eventually this core also collapses to a black hole. Now you've got two black holes sitting here, 40 solar radii apart. Now you just patiently wait for a few billion years, and eventually the binary will merge. And hopefully then you wait for another billion years or so, depending on where it was, for the gravitational waves from this binary to finally reach the Earth and be picked up by the gravitational wave detectors. And if we're lucky enough, then at some point the graduate student in one of my first slides will become extremely happy and will bounce up and down and say, yay, we've detected a gravitational wave. I should say this is not the only way of forming these binaries, and this is actually one of the questions that we're trying as a community to address right now, and in particular I'm very interested in. So there are a few alternatives to this. Remember, the basic problem here is how do you start with these two massive stars which need to get really big at some point, right? Stars can expand by something like a factor of 100 as they age, so they will get to be really big, and yet you need them in the end to end up pretty close together, right? And that's a problem. How do you get things this big in an orbit this small, right? So one way is this thing that I described as the common envelope, where you take the energy out of the binary's orbit, but there are a couple of other ways to do it. One way is a magic wand. Abracadabra, stars, thou shalt not expand. You might think that's very silly, but if you could somehow wave this magic wand, right, it would be great. Because that would tell you, look, I've got two stars, I can just put them close together, close enough that they would efficiently emit gravitational radiation and would merge in a few billion years, even if once they form black holes. But they will never expand, so they will never interact with each other. So that makes life simple, right? How do you create this magic wand? Turns out there may be a way to do that. And we've written with my collaborator Selma de Mink at the University of Amsterdam a paper on this, and several other people have pointed this process out as well quite recently. And the magic wand is very efficient mixing within a star. So we think that there are situations where if you have enough rotation, if the star is rotating very quickly, and one of the ways, by the way, to get that rotation is precisely to be in a closed binary where the companion is exerting tidal forces on you, and that kind of forces you to end up being tidally locked. So you're rotating around your own axis at the same rate as you're going around your companion, so that your tidal bulge is always pointing in the same direction instead of sloshing around, right? Having your tidal bulge, your little beer belly, sloshing around from right to the left is kind of all the time is very inconvenient, energetically unfavorable. Stars don't like that. So they try to settle into this regime where if there is a tidal bulge because you're pulling on me, and so I have developed this beer belly, it's not because I've drunk too much beer, it's because you're pulling on me so hard, then if I'm going on an orbit around you, I kind of want this bulge to always point in the same way towards you, right? And that means that as I'm doing that, I'm going around my own axis at the same rate as I'm going around my orbital companion, right? So if it's a close enough binary, that means I'm actually spinning reasonably quickly. So if I do spin reasonably quickly, then that can enhance the mixing within the star. So instead of the simple picture where I've got a whole bunch of helium in the core of the star and this envelope of hydrogen on the outside, and eventually the helium contracts in the core and the hydrogen expands, I just managed to take all of my hydrogen and mix it up and keep on pouring it in from the outside and putting the helium back to the outside. And so I basically burned through all the hydrogen. So at the end of this process, I just end up with a helium star and nothing else, almost no hydrogen on it. So the helium does start to contract, but there's nothing left to expand. There is no hydrogen left. It's almost all been converted into helium. So this star will just contract in place, will just form a small helium star, won't ever expand, won't ever be tempted to overflow onto its companion. Problem solved. Now you can have two stars close together. There's a third way of doing this. This will require a small demonstration. People in the front row should be very careful. I'm very bad at this. This is about as close as we're going to risk to becoming instrumentalist. So, okay. So we have a binary, right? Two objects, going around each other. Very simple, right? Keep it simple. Yeah. This is my notion. This is my notion of juggling. They're going around each other, and life is boring and unexciting. And then a third object happens to fly by, right? And for a while, these three objects actually interact together. So now, when I tried to pick these up, I didn't realize how large these were. I'm not very good at juggling things this big. Hold on. Let me try this. This is going to be really awkward. Hold on. Okay, now at some point, somebody has to be ready to catch. Are you ready, sir? All right. So at some point, as these three things are going around each other, what will actually happen is, through the action or the gravitational interactions between them, they will actually kick out one of the objects, and kick it out reasonably fast. Nope, not like that. Oops. I missed. I'm sorry, sir. My fault entirely. But you get the apple. Thank you. So we've managed to now kick out one of the objects, and that means that it has taken away quite a bit of energy from the binary. And so the two remaining objects have actually come closer together as a result. So this is a way to bring objects through dynamical interactions closer together. And it turns out there is a place where this is relevant. These places are environments where you have lots and lots of stars packed together very densely. So globular clusters are one particular place where this can happen. Nuclear clusters at the centers of galaxies are another. And this is looks like a very messy plot. It's actually a really beautiful diagram from a paper from some colleagues from Northwestern University. I'm particularly proud of the paper because both of the first two authors were former grad students of mine, even though I wasn't personally involved in this work. But this paper is great. And I really like this particular diagram. And I'm also, okay, the light isn't working, but that's okay. But you get so the idea is basically you've got these three stars. Let's consider them three black holes. So you now have this soup of black holes. These stars weren't necessarily in a binary. They just collapsed into black holes. There's a whole soup of black holes going around. They're interacting with each other. Sometimes they're coming closer together. And as they come closer together, you have some interactions where, let's say, there's a binary going around each other. There's a third object coming by. And as we had in our little juggling example, the third object wanders off with a bit more velocity than it came in with. So it's taken orbital energy from the binary shrinks a bit, as the binary has shrunk a bit, it gets closer and closer together through many, many, many such interactions, as are sketched out over here, until eventually you end up with a binary that's compact enough to be able to merge just through the loss of energy to gravitational waves, right? So this is yet another channel. Now, we don't know what the right channel is at the moment. Maybe all three of these are important. Maybe just one of these is important. Maybe there's something else that people have proposed, a few other things which I haven't mentioned here, as possible channels for forming the kinds of systems that LIGO has detected. So that's one of our obvious goals, figure out how is it that we form these systems that LIGO is detecting. Because there is something really interesting about these systems that LIGO is detecting, right? They're a little bit different from the black holes we've already met in roughly this mass range through observations of systems with matter, right? Remember I said the way you can see black holes electromagnetically is to have some matter around. So in particular, one way to do it is if you have a black hole and another star, and the star is going around the black hole, sometimes you can observationally measure the properties of the orbit in such a system. Typically, these are X-ray binaries because there is material from the other star accreting onto the black hole, and that's generating X-rays. And from these X-ray binary observations, we know a bunch of systems in our galaxy and even a few in other nearby galaxies which have masses around 5 to 15 solar masses. Maybe a little bit more than that, but that's a little bit speculative. Meanwhile, the three LIGO events are over here, right? And so, for example, this event here has two black holes that are roughly 30 solar masses each, merging to make a 60 solar mass black hole. And so this seems a little bit different, right? Do we understand what's special about these? How are they formed? Well, we think we do, but the real question is what can we do with this, right? And this is where this dinosaur comes in, because I like to think of this as a bit of paleontology. Let's call it gravitational wave paleontology, right? So suppose you're a paleontologist, right? And as a paleontologist, you unearth the skull of a dinosaur, right? And that's all you're ever going to get, because you have never seen a living, eating, walking, breathing dinosaur. And yet, if you have the right experience, from the skull, you might be able to figure out what the dinosaur actually looked like when it did walk around, how it behaved, what it ate, how it hunted, how it interacted with other dinosaurs, and so on. So we want to do something similar. For us, these compact objects, these compact binaries, whose mergers LIGO is observing, are like the skulls of the dinosaur, right? What we're trying to see are the remnants at the ends of the lives of massive stars, these neutron stars and the black holes they create. And we want to go back and now do this gravitational wave paleontology and figure out, based on these remnants, what the massive stars were like when they were still happy, vibrant rock stars. Except that it's even more complicated because we don't have a nice little skull like this. Instead, we've got something that looks like this, because we also suffer from very significant measurement uncertainties. It's very hard to piece together all of the information. We only have some particulars about the properties of these binaries well measured. Others are not so well measured. But yet the hope is we can still somehow go and figure out from these simple observations of what stars are like at the ends of their lives, we can maybe figure out all these question marks that are associated with binary evolution. What did the massive stars look like originally, and how they evolved? How did they transfer mass to each other? How much mass did they lose through winds? How did the supernova happen? And ultimately, I think the one thing that is pretty clear, especially now that we have these gravitational wave detections, is actually the last step. Once you have formed the two black holes, how you lose energy and get the binaries to spiral in under the action of gravitational waves. So I think we have quite a bit of work to do, but I also think that this is a very promising way of understanding how stars evolve. Thank you.
Okay, so we have lots of time for questions.
I have two questions. we talk about pairs of black holes coming together and producing gravity waves. But I remember that stars can appear in triples, quadruples. Have we considered black holes coming in triples?
So that's a very good question. Indeed, it's absolutely possible that you may have, for example, a merger of two black holes that are merging still in a system where there is another companion in the system. In general, what's very likely to happen is that the third companion will be in a much wider orbit, so it's going to be only by the time the merger is happening, it's only going to very weakly perturb this merging binary, so there's not likely to be a strong impact on the gravitational wave signal from this merging binary from the outer object. But in principle, it is an interesting question to consider. You're absolutely right.
My question is, what data indicates that it's a black hole at the galaxy center as opposed to dark matter? Is there some sort of rotation or something that...
So dark matter doesn't clump together very well in general because dark matter we think is not very strongly interacting. In principle, people have actually suggested black holes as a possible component of dark matter. So in some sense, you could say that the two questions are actually, it's not a dichotomy, right? Black holes are, for all practical purposes, dark matter. But I think in practice, these kinds of observations don't tell you directly that it really is a black hole. It's just telling you that there is something very dark and very compact and very massive there. There are other attempts by people actually trying to look on very, very, very small scales with, for example, tools like the so-called Event Horizon Telescope, trying to really image the environment very close to the black hole, trying to see, for example, the bending of light from distant stars around the black hole is being lensed by the black hole to actually image the horizon of the black hole, and that will give you potentially a stronger signal that what you're looking at is really a black hole. For the LIGO event, there are also some ways we can tell that these are really black holes as opposed to just being very dense, very massive objects. I mean, one way is that the gravitational waves match so well what general relativity predicts should be the case for the mergers of two black holes. So it would be very strange if we got this fantastic match to theory without this being the right picture. But we also see, for example, this ring down behavior after the merger, and that's a very strong indication that this is really a black hole. You wouldn't expect that if you just took two lumps of matter and stuck them together.
I don't know if I missed this point. Is it necessary for one of the companion stars to become a black hole for them to come together and perhaps give this signal from a gravitational wave?
No, it's not necessary for them for one of them to be a black hole. So you could, for example, have two neutron stars that are coming together. That's actually something we expect eventually to see. We haven't seen it yet, at least as far as I know. If you torture Lisa and Duncan, maybe they will tell you something that I don't know. But as far as I know, there have been no binary neutron stars mergers detected yet. We know that this should happen because we have actually seen pairs of neutron stars in our own galaxy where we see them as pulsars, right? So these neutron stars are rotating. They're not actually pulsing. It's a bit of a misnomer. A pulsar suggests something that's going on and off. Think of it as a lighthouse, right? So here's a beam, a radio beam, and I'm going to be rotating like this. And so now you see me, and now you don't, and now you see me, and now you don't. And I do this very regularly, so you can tell that, my spin period and so on. And then if I'm going in an orbit around something else, then this spin period gets Doppler shifted, right? Because I'm moving towards you a little bit as I'm moving, for example, around this gentleman, and then going away from you as I'm moving on the other side of this gentleman, and so on. So you see the Doppler shifting, so you know now what the properties of the orbit are, and you can actually measure the masses of the two objects, so you know they're both neutron stars, both around 1.5 solar masses, and then you can actually see that the orbit is changing in time exactly consistently with the emission of gravitational waves for some of these systems, because they're pretty close together already, a couple of hours in terms of the orbital period. And we know that if we just wait for another 100 million years or another billion years those particular systems will merge. Now, none of the ones we know in our galaxy will merge in our human lifetime, so these are not individually sources for us. But of course, if we see them in our galaxy, there's every reason to expect there are similar sources in other galaxies, some of which should be merging right about now. And so that means that, yes, we do expect some mergers, for example, coming from 2 neutron stars. Things that are less dense, we won't be able to see just because they won't be in the LIGO band.
This might be there might be a simple answer to this, but earlier in the talk you mentioned that a black hole can only form if the original solar mass is at least 20 solar masses, and then you had a slide more recently that had all these black holes in purple. They were all less than 20 solar masses.
That's right. So these are the masses of the black holes. Not all of the material in the star actually ends up in the black hole. A lot of the material, for example, remember these winds I mentioned that I said were quite significant for these high mass objects? So a lot of the material, for instance, will be lost through winds. Some of the material can be lost during the supernova explosion. So something that looks like a 10 solar mass black hole now could have been a 30 or 40 solar mass star when it was initially born.
All right, thank you.
How often do you expect an event to happen?
So right now, LIGO is detecting a binary black hole roughly once per month of operation, maybe once every 2 months. I mean, given the kind of the rate of events, for example, that happened during the first science run that Lisa had mentioned. In general, this is consistent with the broad picture we had beforehand of how often these things might merge, but until we've actually had these discoveries, we had huge uncertainties, right? In 2010, I tried to write a sort of literature review paper that said, what should LIGO expect to see? And the error bars were about a factor of 1,000, right? Because we really didn't know how often these things happened. It's very difficult to accurately make such predictions. And so this is actually one of the reasons why I'm so excited about these events, because now the fact that we know how often these things happen is already telling us something about how these objects evolve.
My question has to do with general relativistic time dilation. If my understanding is that the deeper you are in a gravitational well, basically time slows down. So how can the black holes actually merge if technically at the event horizon time stops? I've never understood this.
So that's a really good question, right? So I mean, one way to ask this question is, imagine I take this flashlight, or this laser pointer, and I'm not going to turn it on now because I don't want to point it to your eyes. But now imagine I'm a black hole, and this thing is falling in, and I set it up somehow so that it's pulsing once per second, right? So then, as it's falling in, you're absolutely right. From your perspective, there is a time dilation, so you're seeing a pulse once per second, and then once every 10 seconds, and then once every 100 seconds, eventually once a year, and then at some point you wait for 100 years, but you aren't sure, has it really fallen in, or is it just, so strongly dilated? In practice, it doesn't actually stop there, right? It continues moving through. From this point of view, there's nothing special about a black hole horizon. A black hole horizon is a purely imaginary surface. It just goes right in, right? It's just being accelerated by gravity as you normally would expect. All that's happening is that there's this perception of time dilation from your perspective as a distant observer. There is a relative time dilation between things that happen near the horizon and at your location. But in reality, the two objects really are coming together and merging, and there is no stalling of the flashlight as it's approaching the event horizon. Okay. Sorry, I misunderstood your question. Yes, so that's a very good question. So the point there is that the gravitational waves aren't really coming out of the black holes. In fact, nothing can come out of the black holes. The gravitational waves are coming from the orbit. That's where the energy reservoir is. And so it's the region of space, it's the space-time itself outside the black holes that's actually producing this energy that's being emitted in gravitational waves. And yes, in a way, there is a certain amount of redshifting, but that's already included in the full solutions of Einstein's equations that describe the gravitational waves.
When you did the juggling, I remember when a juggler with great skills would juggle 3 apples on every turn, he was able to take a bite out of one of the apples until finally that apple was gone. Is it similar to what happens with 3 black holes?
So black holes typically not, because it's very hard to take a bite out of a black hole without you either sort of completely absorb it or you leave it alone. You cannot pull a little piece out of a black hole. But if you had, for example, a normal star in there, then absolutely you could do that. These are called tidal disruption events. So if you bring a normal star close to a black hole, then if you bring it really close, the whole star can be shredded by the gravity of the black hole. But if you aren't quite so close, you can take a little chunk out of the star, and the star can go on its merry way, but then maybe it's on a very eccentric orbit, returns again, and you can take more and more bites out of the black hole, and absolutely that can happen.
I really liked your talk, especially all the implications about what you can learn about stars from the LIGO observations. But I wondered, can you take that to an extreme statement? Let's say all you knew about the universe and its history were the LIGO observations. You mentioned at the center of galaxies there are multi-million solar mass black holes. Presumably it's possible for those to merge at some point in the history of the universe. The fact that LIGO doesn't see those mergers within a certain time frame, that must have an implication for the history of the universe and the size of the horizon. Are there more? Can you get implications just from LIGO's observations about things about the entire universe? So for instance, wouldn't that imply the universe is finite? At least the horizon is finite, because we're not seeing gigantic mergers of humongous black holes from even, 10 times farther away or 100 times farther away and so on. I just wonder how far you can take that argument.
So specifically regarding the mergers of massive black holes, you don't expect LIGO to see them because the typical frequency scales as 1 over the mass. The mass sends the time scale of the problem, so the frequency is the inverse of that. So frequencies go as 1 over the mass, which means that if you have very massive objects, the frequencies that you're looking at are millihertz or microhertz, depending on the masses, which means LISA is a good detector for them. I don't mean this LISA, I mean the space interferometer that you described, or even pulsar timing arrays that Duncan had mentioned. LIGO won't be able to sense those things, right? So you're absolutely right that non-detections can also provide information. I think right now, none of the upper limits that LIGO has placed are very constraining at this moment, but I think we will increasingly learn from LIGO upper limits just as much as we're learning from the observations. You're absolutely right.
Any other question?
Just a quick question, just to kind of summarize, make sure I have this right. So this process of the black holes colliding could take billions of years, and what we are seeing, it seems like the timescale of the gravitational waves we're seeing is 5 seconds or something, and so but they're probably still emitting these gravitational waves as they slowly combine. The amplitude's too small to predict. Do I have that?
That's absolutely right. It's just a question of the amplitude being too small and the frequency being too low. So again, mentioning the LISA detector, I think you're now in my mind going to be forever associated with the LISA detector, by the way. But the LISA detector could, for example, detect the same black holes that LIGO is seeing, but not at the moment of merger, but instead years, maybe centuries before the merger, when they're still relatively far apart, orbiting each other on our time scales instead of orbiting each other on millisecond time scales. And then potentially you could even detect the same binary first with LISA and then a few years later with LIGO. Then you, of course, get even more information from the combination of those two detections.
Any other questions?
Can we see the...
Wait till you get
Do you think we'll ever be able to detect the black hole at the center of our galaxy?
Well, so I think I would argue that we have in a way detected it, right? We've detected it already through the motions of these stars around it that I showed you using the Keck observations by Andrea Guess's group at UCLA. There are hopes to detect it using this Event Horizon Telescope that I mentioned, which is going to really look at the lensing of light right around the limb of the black hole. But as far as detecting gravitational waves from it, that depends on whether we are lucky and there is, for example, something that's plunging into that massive black hole during the time that the LISA detector is operating. If, for instance, there's a neutron star or black hole that is falling into the black hole at the center of our galaxy, which we think might actually happen once every million years or so, give or take, then if we're really lucky enough that that once every million year event happens while the LISA detector is operating for a few years in the 2030s, then absolutely we would be able to see that merger. With LISA it will be a very loud event. That will be fantastic, but I wouldn't bet on that. So I think gravitational waves are less likely, gravitational wave detections from the black hole at the center of our own galaxy.
I have a question about the frequency of detecting these things and how confident you are that you're detecting all the ones that are passing through us. So if we're looking at the number of events, if there's a big seismic event at the same time that one passes through, are we likely to miss it? So if you could say something about that.
Absolutely. So we're definitely not detecting all the events that we could be detecting because our detectors are not actually running at 100% of the duty cycle, even when they're nominally on. And there are various noisy glitches and artifacts, for example, from earthquakes, as you mentioned, that happen once in a while. So sometimes some of the data has to be vetoed. There are also some locations on the sky where detectors are less sensitive than others. Detectors are kind of, it's not like a telescope where you have to point at a particular location, but still there are areas of greater and lesser sensitivity. So even some very nearby events that should be loud, if they just happen to be in a blind spot of the detectors, will be very difficult to detect. We try to take that all into account when we estimate what is the merger rate in the universe of binary black holes. And so I think, that overall picture is still correct. Of course, if, for instance, LISA through her hard work is able to make the duty cycle increase, we will be able to see more black holes per unit time. Or if the detectors become more sensitive, we'll be able to see more black holes per unit time, and that, of course, would be great.
I have a question going back to the previous question. So there are galaxies that do merge. And so do those black holes at their centers merge? And if so, could they be detected?
Absolutely. So the expectation indeed is that as two galaxies merge, most galaxies host a massive or supermassive black hole at their center. Those massive or supermassive black holes should come close together. There are some concerns about whether they really will merge. I think right now the consensus is yes, probably, but with some caveats, because when the two black holes get so close together, there are very few stars left around in their vicinity, but not yet close enough together to where gravitational waves are strong. They might sort of get stuck there, so there's a little bit of a concern there, but we think that indeed there should be massive black hole mergers, and LIGO isn't the right instrument for them. The frequencies will be too low, but LISA and pulsar timing arrays ought to be able to see them. Pulsar timing arrays are actively looking now. LISA, of course, hasn't been launched yet, but pulsar timing arrays are right now, so far, just providing upper limits on the frequency of these mergers. They haven't yet been able to make a detection.
Final question over here. Just not a question. I wanted to expand on a final comment. So I wanted to expand on Ilya's answer to the previous question, how many of those events we may be missing, let's say, every year. So imagine you would have ideal instrument that would see all the way to Big Bang, that would see entire universe. You probably could see up to 1 million of those events a year. Okay, Ilya probably would say 10 to 5, 100,000. Somewhere between 100,000 and 1 million a year would happen when we see 1 or 2 or 3 right now. So increasing sensitivity can bring us to much higher numbers.
Thank you, Chris.
Thanks, Ilya.
Thank you.